All right, ladies and gentlemen, class recording has started. So, yesterday, we introduced the topic of mechanics. And like its name, or like the subtitle on the board suggests, the study of motion. And so we said that if we're trying to describe the motion of an object, there are four things that we want to know about that motion. What do we want to know about the motion if we're trying to describe it? Carlos, what's one thing?
Where it is.
Where it is. What else? Sam, what is it doing? Dahlia, what else? What's it going to do next? And finally,
Where does it go? Or which way?
that's more, that which way is it going, we'll find actually gets wrapped into what is it doing. We'll see that in a second. Alexander, when, what time are all these things happening? So if we can answer those four questions, we do a good job of describing motion. And I kind of mentioned to you guys yesterday that this unit is all about just describing motion. So we're going to deal with facts and laws. We'll get into the theory part next unit when we talk about forces. We'll talk about the why in the next unit. But here we're just describing things, okay? So, something to keep in mind, okay, when we talk about the importance of language, okay? A lot of times I know like you guys do English and you do vocab in English and all those fun things. There's definitely an important vocab component that goes along with this unit especially. Today, we're going to introduce a bunch of things that are words that you probably have heard before, like speed and velocity. But those words have specific meanings. They're different from each other, okay? And so we need to keep in things like displacement and distance travel. Sound similar, but they're different. They have specific meanings. And so make sure during this beginning unit we get those vocab words down and we understand the subtle differences between them, because it's going to be important moving forward when we talk about analyzing motion. If you can't tell the difference between speed and velocity, it's going to make it hard for you to analyze that motion, or more importantly, answer questions on quizzes and stuff like that, okay? So with that in mind, let's go forward, okay? So yesterday we introduced two new terms. What are the two new terms that we introduced yesterday? What's the first one? That's sort of an ancillary thing. But yes, we did talk about that. I was thinking something more higher up on the page than that. What's the first new description we learned yesterday? What do we use the reference point for again? Something else I wanted to talk about, Sam. The frame of reference we use to describe an object's position, okay? So the first thing we introduced yesterday was the position, and that is the answer to the question, where is the object? But we spent a lot of time talking, in order to describe the position, we need a reference point, we need a frame of reference, because we can't describe the position unless we describe it in relation to other things, okay? We talked yesterday that we're going to limit our motion. What kind of motion are we going to talk about here in just this unit? One-dimensional motion, which is a fancy way of saying moving along what? A number line, or the x-axis, right? We may see, Jack will get into some situations where we're moving along the y-axis, but only one axis at a time, right? So straight lines. And we talked about the idea that our frame of reference out along a straight line, generally speaking, looks like a number line. We have a 0 point, we call one way positive, we call one way negative to distinguish that way from this way. And that's all we have to worry about, because on a straight line, we only have those two options, okay? So position, where is the object? But then we got into getting into, well, what if the position changes? What do we call a change in the position?
Movement.
Displacement, all right? So when we talk about describing the change in its position, we talk about its displacement, all right? When we're calculating the displacement, we're concerned with two things. What two things do we need to know in order to calculate the displacement of an object?
Where it is and where it was.
Easy, man. Hey, there's people that are raising their hands, and I realize you're not paying attention, but, you know, other people need to participate too, okay? So, all right. Dahlia, go ahead. The magnitude and the direction is sort of the end result of what we need to know. Actually, Carlos, what do we need to know to describe the displacement?
Where it is and where it was.
Where it is and where it was, right? We need to know where it starts and where it finishes. That's the definition of displacement. The difference between where it ends up versus where it started, okay? Now, to accurately describe that, we're going to need to describe two things, right? Dahlia, what are the two things we need to describe if we're describing its motion? The magnitude and the direction. Magnitude is a fancy word for what? How much or how big something is, right? And then direction is a fancy word for which way, the direction. Because this displacement was different than this displacement, right? Two things. One, negative 64. I think you guys might have had negative 63, but in the other class we decided we want negative 64, whatever, okay? So negative 63 versus positive 60, right? First obvious difference is what? Negative 64 versus positive 60. The positive and negative, and Izzy, that describes for us what? Right and left, which direction the lizard was going, right? But the other thing that's different is the magnitude, right? This has a magnitude of 60. The magnitude of this one is 64. Which one is a bigger displacement? 64, even though it has the negative sign in front of it, right? We said, yeah, my warning to you yesterday was the negative sign, we use it for what? Direction. It doesn't tell us anything about how big or small something is. It's just a direction, okay? Good there? All right. Flip it over to the back side, or sorry, the back of page 2. There's a picture of a man and a car, okay? And so the story goes like this. It says, a man starts out from his house and drives east 50 kilometers. After that, his car runs out of gas. He walks the next 5 kilometers until he reaches a gas station. He sits at the gas station for 30 minutes to fill his gas can and get something cold to drink. He walks back 3 kilometers west, or he walks back west for 3 kilometers. But then a kindly stranger gives him a ride the remaining 2 kilometers to get back to his car. When he finally reaches his car, he drives back west 50 kilometers to arrive back at his house. Okay? So, first thing I have to take care of, because I know there's at least one person in this room that is going to, question this story. Like, so people bring up, well, why? Why did he just drive this way and then drive back to his house? Right? Well, here's the deal. He was actually on his way to a blind date, and because his car ran out of gas and he had to walk and he filled up, he missed his blind date, so he had to go back home. So this is a story about the lost opportunity for love. That's what it's about. So just so you know. So if there's more context there now. People get mad. We're like, why did you just drive that way and then drive back to his house? Well, he missed his chance at true love, so what else are you going to do? Go home. That's basically it. All right, so 4 questions about this story. Why don't you talk to the person next to you for about 2 minutes and come up with some answers for those 4 questions out at the bottom. Go. His starting point, the starting point of his trip. Yes, starting from the reference point. Yeah, starting from the reference. Yeah, throughout the whole story, think of his starting point as like his whole trip and where he started his actual trip at. Okay? Not each individual leg of his trip, but the trip as a whole. Okay? I don't want you to worry about it. I don't want you to worry about it. The stranger was some kind of psychopath or something like that. He's a kindly stranger. for the whole trip, not just individual legs of the trip, divided for its whole trip. All right, you ready to talk? Okay. So, man's displacement when his car runs on gas. What's our answer? Positive 50 kilometers, right? What could also be a acceptable answer for that question? I suppose negative is an acceptable answer. That wasn't what I was thinking of, but it could be. Displacement is a vector. It means a magnitude and a direction, right? What else could we have used for the direction in this problem? East, right? It does give you some directions in that problem. So 50 kilometers east would have worked as well, because it did specifically tell you that in this problem, okay? And that would take care of the direction, okay? All right, displacement when he arrives at the gas station. Positive 55 kilometers, right? He is now 55 kilometers from his starting point, okay? Good there. All right, here's where things start getting a little bit tricky, okay? Displacement when the kindly stranger gives him a ride. Positive 52, okay? Even though he went back towards the way he came from, he's still on the positive side of where he started. Does that make sense? Right? If we call east positive, he's still 52 kilometers to the east of where he started. So his displacement for the trip is positive 52. Okay? Yes, go. Okay, hold on a second. Did you want to answer the last one? Okay. All right, so I'll let Jennifer do it because you've answered lots of questions. I want to make sure other people get involved. So, Jennifer, last question. What's his displacement for his entire trip? Positive or negative 0, although if we can just go with 0 on that one because 0 doesn't have a direction, it just is, right? So in that case, right, where in the case for his entire trip, where does he end up? Back home. Back where he started. What's the difference between his starting point and his ending point? Nothing, right? So his displacement is 0, okay? Good there, okay? Now, saying that the displacement of his trip is 0 doesn't really tell the story of his whole day, right? It doesn't tell the story about the anguish that he felt when his car ran out of gas, right? And the disappointment as he was walking to the gas station, you know, when he realized he was going to miss his blind date, right? Or the, you know, thanks that he felt, or the, you know, I don't know, what was the word I'm thinking of? Gratitude. That was the word I was thinking of. The gratitude he felt when the kindly stranger picked him up and drove him back to his car, right? Or the resignment that he's just going to have to go home now, and you know he may have missed his chance, right? Saying that his displacement for his entire trip is 0 doesn't convey that message, right? So sometimes we don't just want to know where we started and where we finished. Sometimes we have to tell the middle part of the story as well. And so while displacement is a change in position, sometimes we need to know more than that. And so we take a look at distance traveled. All right? So distance traveled is the length of the total trip taken between a starting point and an ending point. When we're talking about displacement, does the path we take to get to the end point matter? Nope. When we're talking about displacement, all that matters is where we started and where we finished. But sometimes we need to know the total trip. Sometimes we need to know how far did we actually go, right? Give it a couple years, you'll start driving, right? If you're lucky enough to have your own car, you'll leave home in the morning. You'll drive to school. After school, you may drive to practice somewhere. Practice is off campus, right? Or you may drive to a job that you go to after school. You may drive over to a friend's house to work for the day or do some homework or a project you have to work on. And then ultimately you end up back at home, right? What would be your displacement of the entire day? 0, right? But there's a little measurement device on your car that tracks your mileage, right? We call it the odometer. Does the odometer measure displacement? No. It's measuring what? Distance traveled. It takes into account the entire path that you go on for the whole day, right? So, if we revisit this situation, right? But now the 4 questions have changed. What is the man's distance traveled when his car runs out of gas? So take a minute, answer those 4 questions, then we'll come back and talk again. Go. Like you said, I like that enthusiasm. All right, so let's fill in some of these lines here, okay? What is the man's distance traveled when his car runs out of gas? 50 kilometers. Okay. What is the man's distance traveled when he arrives at the gas station? 55 kilometers. What's the distance traveled when the kindly stranger picks him up? 58. Because remember, he walks the 3 kilometers, then the stranger picks him up and drives him the other 2 to get back to his car, right? And then, distance traveled for his entire trip, 110 kilometers. Okay. Good with those 4? So, sometimes distance and displacement are the same. Sometimes they're not. When are distance and displacement going to be the same? When you only go one direction, distance and displacement will be the same. But as soon as you change directions, right, now they become different. And that's true when we're going in one dimension, but it's also true when we break out into 2 dimensions or 3 dimensions, right? If you always go the same direction, then distance and displacement will be the same. But as soon as you change, that becomes different, okay? What else is different about my recording or my measurements of distance traveled versus displacement? They did get bigger every time. Distance traveled is always going to get bigger. What else? Is there any direction up there? Does it matter what direction we're going before we're talking about distance? No. Distance traveled is our first example of a scalar quantity. It's not scalar, it's scalar. Okay? Scalar quantities only tell us magnitude, which means they only tell us what? How much or how big. Okay? Scalar quantities only tell us magnitude. They don't have direction. Okay? There are other scalar quantities that we will run into as we go through this course, right? Things like mass. Mass doesn't have a direction, it's just how much of something, right? Things like time. Time doesn't have direction, it's just how long something takes, right? So scalar quantities only tell us magnitude. Okay? Good there? All right. So that's the first question that we talk about when we're talking about measuring motion, right? Where is the object? What was the next question and the next thing we said we wanted to know? What is it doing? Those are kind of two different. Where is it going is not quite descriptive enough. We need a little bit more than that, okay? So the next question that we want to look into is, what is the object doing right now? Again, there are two ways we can describe this, okay? First, we describe its speed, okay? The rate at which distance is traveled. Thinking about going back to math class, and we'll talk about this several times throughout the year, okay? When we describe something as a rate, that implies that we are comparing it to what? Yes, but there's something specific that other thing is. Whenever we describe something as a rate, what are we comparing it to? If you read the definition that's up on the board, you might be able to figure it out. Whenever we describe something as a rate, what are we looking at or comparing it to? Time, right? How long does it take? Whatever we describe as a rate, we're always comparing it to time, or how long does it take, right? So speed is the ratio of the distance an object moves and the time it takes to move that distance, okay? How do we represent ratios mathematically? Fractions, right? So Jack, what does this ratio look like if we're representing it as a fraction? You've seen it before in math class, right? If it's a ratio of distance to time, what does it look like? Distance over time, right? E over T. And that ratio is the speed. Okay? Good there? What does this not tell us? Right? This tells us how far it went and how long it took. But it doesn't tell us what direction it's going, right? Remember yesterday when we said you were trying to describe to your friend because you saw a creepy clown guy walking on the street, right? And you wanted to warn your friend about it. An important thing that your friend might want to know is what direction they're going, right? The creepy clown guy is going and how fast is going. Speed tells you what? How fast. So then we have to have a way to figure out the direction. And that's when we get into the average velocity. Okay? It's on the other side. We'll do these calculations here in a second. Okay? So, all right. Velocity, or average velocity, is defined as the rate of displacement of an object. We just said, anytime you compare something or describe something as a rate, what are you comparing it to? Time. Right? So a ratio between the displacement of an object and the time it takes to complete that displacement. So if we want to build a mathematical relationship here, right? It's a ratio. Jack, ratios look like what? Fractions. What's going to be on the top of this fraction for velocity? Anyone help him? Displacement. Marissa, do you remember what we used to represent displacement, the notation we used to represent displacement? It's on the front page of your outline. Delta what? Delta x, right? Remember, Dahlia, the delta in general means what? Change, okay? The delta in general means change. Sorry, that's a bad triangle. Right? Whatever we put the triangle in front of, that's what we're representing the change in. We define displacement way back on the first page as change in position. Change in where we are on the x-axis, okay? And we're comparing that to what? Okay? And that's how we figure out the average velocity. So V is equal to delta x over t. Okay? Good there? All right. Flip it back to the previous page. Here's a picture of a girl running a 100-meter race. All right? A certain portion of that race has been timed. Here she is at the starting line. Here she is 50 meters away from the starting line. If we look at these stopwatches, the stopwatch read 0 when she was at the starting line. It's now reading 6 seconds when she's at the 50-meter mark, right? So we said that in order to calculate the speed of something, we need to know two things. What do we need to know? Time and distance, right? So S is equal to D over T, right? What's the distance that she travels here? 50 meters, or at least the distance that we have the time for, right? So in this case here, that's going to be 50 meters. This is a little tricky. How many significant digits does that measurement have? It have 2. Okay? Does it have 2 the way that it's written right now? What would I have to do to this? Okay. I know you know the answers, but other people need the answers too. Right? So here's my two significant digits, right? What's the time? Right? In this case here, we have 1, 2, 3, 4, 5, 6, and 7. Right? So this is my certain digit, right? But then Alexander, what would I have to add on the end of that? 0.0, right? Because that's my uncertain digit. Okay? Plug that into your calculator real quick. What do you get? Okay. So actually, when it comes out, what does it come out as? It comes out 8.3333333333. But here, how many significant digits on the top of this measurement, or the top of this calculation? 2. How many here? 2. When we're dividing, we look at the least total number. They're both 2, so we would round that then to 8.3. Okay. Oh, are we good on units? Sorry. We understand why that's the unit, right? Because speed is a derived number, right? We just mash the 2 units together. So we have meters on the top, seconds on the bottom, meters per second. Okay? Good there? All right. On the back side, you have a picture of the same lizard that we had from before, okay? Making his same trip. So if we look on the front side, I believe we called this first displacement positive 60 centimeters. Is that what we called it on the front side? Yeah. Okay. And then this second displacement we called negative 63 centimeters. Is that right? Is that what you got? Is that what the calculation that you got? Yes? Okay. All right. If it says average velocity, we need to know 2 things, right? We need to know the displacement, but we also need to know what? To calculate the velocity, velocity is a relationship between which 2 things? Time and displacement, right? We got our displacements, let's get our times, okay? So here, this first trip, when the lizard was at the beginning point, the clock was reading 0. When it's at its ending point, that clock now is reading what? What is this stopwatch say right here? 4, right? Except for this case here, right? Because, right, certain digits are the single numbers, we probably should go 4.0, right? Technically, this should be 60 plus, yes, or 60 points, okay? Good there? Okay. This one down here, this is a little bit later on. The lizard starts this back trip at 6 on the clock and ends up the back trip at 9 on the clock. So what is the time that that trip takes? Okay, good there? Understand where those came from? All right, so to calculate the velocity, right? Delta x over delta t. What's delta x for the blue trip? Sorry, the top one. What did we say this displacement was of this blue trip? 60, but what? What's important when we're talking about displacement? Positive 60, right? Divided by 4 seconds. Okay? Does that make sense? When you plug those same numbers into this equation for the red trip, we end up with negative 21 centimeters per second. That's it. Is that good? I just did that real fast because I was getting close to the end of the period. So, yeah. Does that make sense? We'll finish that up tomorrow, and then we'll talk about acceleration before your quiz, okay? Don't forget, quiz tomorrow will be open notes because we're still kind of early in this section, okay?